So recall there are two ways of combining resistors. Yeah. So if you have two or more in series, and to be in series, there is no branch between them. Then this can be replaced with a single resistor, R3, where R3, or R equivalence, is equal to just R1 plus R2. And you could also have them in parallel. And they can be replaced with a single resistor, so this would be parallel. And R3 would be 1 over R1 plus 1 over R2. And to tell if they're in parallel, you can connect both sides without running through another resistor or any other device. So you can connect this terminal with that terminal and that terminal with that terminal. So, find the circuit. Here we go. So I have a 10-volt battery. We have 6 ohm here. And as you draw these, you will get messier and messier in drawing resistors. As basically the problem technique is literally combine 2 resistors and redraw the whole thing. If you're working in pencil, you can erase to do it. That might be easier, but in a little bit, we're going to go backwards. That was supposed to be connected here, but it makes literally no difference. So this will be 4 ohm. This will be 8 ohm. I need to stop putting tells on it. It's just a force of habit because that's how I write it. But this is neater whenever I... Alright. So, a little note too. For series, the same current passes through the components. So if I have in series R1, R2, and the current coming into this is I, then the current going through this resistor would be I, and the current going through this resistor would be I. What do you think about parallel?
CJ Emerson.
What do you think they share? The same voltage drop is over the component. I don't like how that worded that. Each component has the same voltage drop. And I'll draw it like this. So if the voltage up here was V2 and the voltage down here is V1, then the voltage is the same everywhere on this line. And the voltage over here is the same all the way on this line. So the voltage drop going through this resistor would be V2 and V1 here, and the voltage drop across this resistor will go from V2 to V1 here. So things in series share the same current. Things in parallel share the same voltage. Which, if we analyze something in series, so let me do something. So this would be for a parallel. Let's suppose I have a 10 ohm and a 5 ohm. And this is hooked up to 60 volts. And this goes to your terminal of the battery, which would be at 0 volts. So altogether, I have a 60 volt drop. You can connect this to a 60 volt battery and have it done something like this, so you can have a complete circuit. Where this would be 60 volts, that would be 10 ohms, and that would be 5 ohms. You should recognize this being in series. This is equivalent to a circuit connected to a 15 ohm resistor, right? And thus the current leaving out of this would be what? Yes. So this is equivalent to 4 amps coming out of there. Now these two circuits are the exact same. There's no difference between them, really. That means 4 amps is coming out right here. What would be the voltage drop across this resistor? Yes. Remember there, our Ohm's law. Voltage is equal to current times resistance. So this would be the plus and this would be the minus side. So this will be 40 volts across this resistor. Which means if you were to remove this resistor and just have these 2 points as the terminal of a battery, it'd be equivalent to a 40 volt battery. So 60 volts with a 5 ohm resistor would give you 40 volts. And what would be the voltage drop across this resistor? The top would be plus, the bottom would be minus. So it's written like this, whereas the top of this battery is plus and the bottom of it is minus. You'll notice they're in opposite directions. We'll get to that later. So 4 times 5 is 20 volts. You'll notice 40 volts, 20 volts is 60 volts. So we dropped by 60 volts, and we end up with 60 volts battery. So we dropped to 0. So the negative side of the battery would be at 0 volts. The top side of the battery would be at 60 volts, and then we drop down. So resistors consume voltage, basically. And they resist current flow. So I think they're related. Voltage and current are linear to each other, linear by this proportionality constant, R, resistance. So what do we do first in this circuit? Alright, what two are in series? So these two are in series. We can replace it. And I hope you love drawing these circuits. As if you haven't told by the size of this problem, how many times we're going to end up drawing this if we're choosing to at a time every single time. Alright, so we replace these two. I'm replacing it right there. 10 plus 2, 12 ohms. I have 6 ohms, I have 8 ohms. Very, very, very easy to make a mistake. Not only can you accidentally draw the diagram wrong, you can put the wrong numbers in it. Alright, now what do we do? Our series. So which two are in series or parallel? And then tell me what if it is series or parallel. So pick two and tell me which two, what to do. If you can connect any two without passing through another resistor, if you can connect both sides of it, they're in parallel. Yes, the top right corners. So what does this one connect all to? Well, it connects here, it connects here, it connects here, and it connects right there. This side of it can go down and connect right here, or it can go all the way down and connect right here. You should already be able to see that the 6 and the 12 are connected by the same set of wires. These can connect right here to here, and here to here. These can connect to this one, or this one can connect to that one, or that one can connect to that one, or they can connect to the battery. And this 4 can connect to the 6, the 4 can also connect to the 8, or the 6 and the 8 can connect. And the battery is connected to this one right here. So we can see the only parallel ones are the 6 and 12. They both use the green and yellow wires. No other two has the same two set of colors. Though you're going to need to learn how to do this without colors. We can see that the 6 can come over here and connect right here. So I didn't pass through any other resistors to go from this side of the 6 to that side. And then I can come over here to the opposite side without passing through any other resistors and connect it right here. So both sides of these two resistors can be connected without going through. So these two are in parallel. So we do 1 over 6 plus 1 over 12. That would be 2 over 12 plus 1 over 12 which is going to be equal to 1 over 3 over 12, which is equal to 12 over 3, which is equal to 4. So replacing these,
We need your story in
uh,
there, and then I just have to have you sign for it. Should be, you're like,
I'll put
you didn't, because you're not reading. You're
Yeah.
just gonna
babysit, basically.
read the directions, go,
Yeah.
that's it, yeah.
Yeah. Mm-hmm. So these two, they connect right here and right here. So I can replace both of these with a single resistor right here that is equal to 4 ohms. Make sense? You see how I did it? I could have also, again, if I have 2 points right here and here, I could have drawn this any way I wanted to. I could have made it a straight line. As long as I have just one resistor connecting between it. So this is 8 right here, 6 right here, 4 right here, 8 right here, and it might be easier to stop putting ohms. Symbol 2. As you know, these are all resistors. And now what do we do? Which two? So yeah, the one right, 8 plus 4, so these are in series. That gives us 12. So they connect right here and right here. So right here and right here. So I'm going to draw it right here. That is 12 ohms. 8 plus 4. All right. Which two now? Parallel. So I can go right here. That connects the top of each, and I can connect the bottom of each. So these are in parallel. 6 and 12 we've already done. That gives us 4. And they connect right here and right here. So right here and right here, I'm going to replace with a single resistor. That would be equal to 4 ohms. Those two can be replaced right here. All right. Now which two? Series, so 4 and 4. So they connect right here and right here. So I can replace that one. 1 right here. And that'll be 8. 4 plus 4 is 8. Now which two? Alright. Here's a little trick. If you have 2 resistors, I'll come here and do that. So 1 over 8 plus 1 over 8. That'll give you 2 8s on the bottom, which will give you 8 over 2, so it's equal to 4. If they're the same value, it's just going to be half of them. The reason why that is if you have I current, and one side is not more, if you have the same resistance on both sides, the current is going to equally split and go down both. If you had almost no resistance down here, the current is going to choose to go through the path of least resistance. So this would be equivalent to 4 ohms. And we're almost done with part 1. So I can connect this right here with a single resistor that has a value of 4. Now what is? Yep, no branches in between. That's 8. Eight ohms right here. This is 8 ohms. And I have my 6 right here. There's a branch right here. So going up here, I can connect the top 2 without going through any resistors. And I can connect the bottom 2, so that means they're in parallel. Yeah. So 8 and 8 gives us 4. And the last one is very simple. It is 10. So all of this is equivalent to this circuit right here with 10 ohms right here. So how much current is leaving the battery? 1 amp. So 1 amp is leaving the battery. Now all of these circuits are the exact same circuit. That means 1 amp leaving this battery. How much voltage drops across this 6 ohm resistor? So voltage is equal to current times resistance. So 1 amp times 6, we get 6 volts. Note, this 6 ohm resistor is the same resistor used in the entire problem. So going back up to the original circuit, we have 1 amp, and we're going to have a 6 volt drop. And this is the plus side, that's the minus. This will be thus the plus side here. We do opposite of the direction of the battery. Because we're going to go from 10 volts here to 6 volts basically. 4 volts. That means this was the positive, this is the lower side. Does that make sense? So we dropped by 6 volts. This is the voltage drop. 6 volts. We're going from 10 volts to 4 volts. Alright, so we're going up here. We have 10 volts, 1 amp. We have a voltage drop across the resistor, 6 volts. We have a current through this resistor that is also 1 amp. Alright. So, what would be the voltage drop and current through here? Yes. So, we see we're dropping by 6, which would mean this point right here, and you think of the negative side as being 0 volts. This would have to be 4 volts here, which gives both of these a 4 volt voltage drop. A 4 volt voltage drop. And we know current is equal to voltage over resistance. So 4 divided by 8, that's a half an amp. And this will be half an amp. And this 8 resistor is the same throughout here. So you should know that this is a 4 volt voltage here. And we have 0.5 amps going through here. Now then, if we started out right here with 1 amp going up to this branch, so we have 1 amp going in right here, and half an amp decides to go downward.
Excuse me, teachers, can I get you to post your first and second period attendance, please? We've got several that have not posted first and second.
How much
Thank
How
you.
much current must be going through here? So imagine you have a river. So we have a river, and you poured 1 liter of dye, and it flowed in this direction. And over here, you collect in a bucket half a liter going down here. You start out with 1 liter of Mountain Dew, let's say, and you end up with half a liter of Mountain Dew here. How much would be over in this direction? It would have to be half a liter. This is called Kirchhoff's current law. Kirchhoff's current law. The sum of current entering a branch must equal the sum of current leaving the branch. You can't just magically have current disappear. Conservation of charge is another name for it, but it's usually just called Kirchhoff's current law. So if you have, I label this current I1, and label this I2 and that I3, then I1 has to equal I2 plus I3. If I instead labeled this I1, this I2, and that I3, then the current entering this node, and this is called a node or a branch, or intersection. So node, branch, intersection, they're all interchangeable. Then here we have I1 plus I2 has to equal I3. Or if you had something crazy where I1, I2, I3, and I4, then the sum going into has to equal the sum leaving. Make sense? So you should know that this is 0.5 amps also. What would be the voltage drop across of it? So it would be 2 volts. So we know that the current, if 0.5 amps comes down here, 0.5 amps goes down here. We also know, looking at this one, again, this is the same as this one, so it's 0.5 amps. And going around here would have to be 0.5 amps. And we know the voltage drop here was 2 volts. Which means, so again, we start right here at 10 volts. We're going to drop 6 volts, which means right here has to be 4 volts. And then we drop another 2 volts across this one, so right here has to be 2 volts. And this point right here is all 0 volts. So the voltage drop across this resistor would have to be 2 volts, right? And these are in parallel, so the voltage drop here has to be 2 volts. Voltage drop here has to be 2 volts. And to figure out current, it's voltage divided by resistance. So the current going through here would be 2 divided by 8, which would be 0.25 amps. This would be 2 divided by 8, so 0.25 amps. And this 8 right here, this resistor right here, never changed throughout this whole problem. So this would have to be 0.25 amps. And it should have a voltage drop of 2 volts. And I guess I should label this node is at 2 volts. This node here is at 0 volts. This node here is at 4 volts. So you can clearly see right here, 4 volts. Usually we don't label the node with a voltage, but it might help. This problem was way too long to be using as an example to explain this. But if we continue it through, I'm hoping you at least see how to do these problems. I don't think we'll end up using Kirchhoff's voltage law in this one. And I want to go over it too. I don't think this one needs Kirchhoff's voltage law. So I'm going to, basically you can continue working this the same way. I want to explain Kirchhoff's voltage law too. As these two are very helpful when you get into a situation where Ohm's law fails to give you the answer. Most of these problems you use just Ohm's law. The sum of voltages around a loop add to 0. So if we have a voltage V, I'll call it Vs as voltage source. Remember that the long side is your positive terminal, and the short side is the negative terminal. And if you draw a resistor, then the more positive side, so this would be Vs and this would be 0 down here, gets the positive terminal, and the lower side gets the negative. So if I draw a loop, I'll draw it clockwise, I go around it, then if you go from minus to plus on a battery, I hope this is right. It doesn't matter if it's right or wrong. It'll still work out mathematically. Then you add the voltage. And if you go from plus to minus on a resistor, you subtract the resistance. Or subtract the voltage drop, I mean. You would subtract, and also, this would have a voltage of the resistor, which is equal to the current going through the resistor times the resistance. Likewise, if you do the opposite, if you go from minus to plus, then you would add the voltage across the resistor. Or if you go from backwards, if you go from plus to minus, then you subtract the voltage. So if you this would be going left to right. So going around here, we see that we would add Vs, and we'll say that the current leaving this battery is I. We subtract IR, and that has equal 0. So what this tells us is that solving for, let's say, I, Vs would have to be equal to I times R, and thus the current would be equal to your voltage source divided by your resistor. The usefulness of this is it does not matter any loop you use. So I will call this Vs. I will call this Is. I'll call this R1. I'll call this R2. Call this R3. You should recognize, okay, and this would be I1, and this would be I2, and this would be I3. And obviously this would have a voltage drop of V3, this would have a voltage drop of V1, and this would have a voltage drop of V2. Make sense? So you should recognize what is I3. You should recognize that I3 is the same current as the battery producing. Yes, this is going to diverge, but remember, the same current going into the branch will be the same current coming out of the branch. And also, these two are connected in series, and anything connected in series shares the same current. But going around, you can go around the loop like this. So I'm taking the bottom path. So I have, this would be my plus, that'd be my minus, that'd be my plus, that'd be my minus. So you would have Vs. So the loop is like this. Vs minus V1 minus V3 has to equal 0. Or another way is I1 times V1, and I1 times R1 minus I3 R3 has to equal 0. These are the two same equations. Now I'll call this loop 1. You could have also done this loop going around the top. That's another loop. So you can go all the way around here. I call that loop 2. So that's Vs. That is R1, R2, and R3. So Vs minus V2 minus V3 has to equal 0. Or writing it in terms of current, that'd be I2 times R2 minus I3 times R3 equals 0. That's loop 2. And we'll do the last loop. You could, but I just meant for this one circuit. The other loop is the first obvious loop you see inside here. So this is plus minus, that's plus minus, R2 and R1. So going this way, I go plus minus. So that means I'm going from plus to minus, I would subtract it. So it'd be minus B2. And going here, I'm going from minus to plus in this direction. So I'd add V1, that has the equal 0. Or equivalently, this is equivalently saying that the voltage V1 is equal to V2, right? Which we already knew that things in parallel have the same voltage. Then you can also do this. So we have IS, and it's converting into I2 and I1. Kirchhoff's law says that IS is equal to I1 plus I2. We also have this situation where I2 is merging and I1 is merging the R3. So I1 plus I2 is equal to I3. Which, here you should see that I1 and I2 is IS. So IS is equal to I3. How many equations do we have? A lot. But we also have a lot of unknowns, and we can use them. You don't have to come up and use every single equation. Most of the time, it's not necessary. But you do have them at your disposal if you get stuck. So you can generate lots and lots of algebraic expressions and equations. And as long as you know so you can always take like a V2 and then turn it into I2, R2. If you know what Vs is and V3 is, then you could, or maybe you knew what V2 and Vs is, then you could solve for V3. You can always solve for unknown. So the other technique besides Kirchhoff's laws is to just go all the way back up, which if you see on this problem, the amount of steps you have is a lot. We could have used Kirchhoff's laws right here instead of looking and analyzing this portion right here to get it. You could have recognized, like if you didn't know the voltage here and the current here, you could have made a loop around here and then solve for the voltage here. Does that make sense? Because if you know all the information on this resistor, all the information on this resistor, and if you can draw a loop right here and you have one unknown thing about the resistor, as long as you know the resistance of it, then you can solve for voltage. And from voltage and resistance, you can solve for current. I'm trying to see if there's anything I could have done there. I need to know the current going through that one. So looking at this one, I know that I have 0.5 amps going to the right through here. I know I have 0.25 amps going down right here. So how much current is going through here? Yeah. So that means this 4 ohm resistor right here would have to have 0.25 amps. And that's the same thing. You can keep going all the way back up. 0.5 up here, 0.25 here, 0.25 amps here, and thus we have 0.25 amps here. Figure out voltage, it'd be a quarter times 4, so we get 1 amp here. Which makes no sense. Wait, is that right? That's not right. Was I trying to rush it too much? Oh, no. I was doing voltage right there. I was right. That then tells you we have a 1 volt drop right here. And then we can play, if you wanted to, we can continue the step, or we can do Kirchhoff's voltage law to cheat. You can draw a loop to where you go through this resistor, and then down through this resistor, and back that way. Here's a loop. It's a random loop going from here, here. And thus we can use that loop to figure out what the voltage is here. Then we can do another loop, figure out the, you wouldn't be able to use a loop, but you could use a loop to calculate this. I personally wouldn't. I would just continue using Beer of Ohm's law and just go back up. But the point is, for every step, you can, once you figure out one information, that never changes. You just go all the way back up and label it. Obviously, the thing that makes it the easiest, don't draw super small. Use lots and lots of paper. Try to draw as neat as possible so you can go back and do it. This was a big problem